right, well, thanks very much for the invitation. I'm very happy to be here. As was mentioned, I need to leave to go teach at MIT immediately at the end of this, but I will be back later in the afternoon and in the evening. So, if there are any questions that we don't have time for now, feel free to ask them later. I was asked to do this on somewhat short notice, and my understanding is the audience here has a pretty diverse range of backgrounds. So to the people for whom a lot of what I say is very familiar, my apologies. To the people to whom a lot of what I say is pretty new, please feel free to ask questions as I go, ask me about stuff that isn't unclear. All right, so I was asked to talk about CMB physics, which I reframed into my own interest of what things we can learn about dark matter from the CMB. So I want to start by just talking a little bit about what we've already learned from the CMB, about the CMB's about all the cool things the CMB can do as a probe for new physics, and then focus in on the area that I have spent the most time working on, which is understanding how the CMB can constrain energy transfer from the dark sector into the visible sector. So of course, the first thing, so the cosmic microwave background is light that was emitted when the universe was only around 400,000 years old, around redshifts of 1,000 to one significant figure. It's that I'm sure you have all seen the beautiful picture from the European Space Agency in Planck showing the anisotropies in the cosmic microwave background across the sky. Over the last 30+ years, we have measured those anisotropies with extreme precision, and it has told us a lot about the universe. The CMB encodes information about, so the redshift 1,000 was when the universe went from being almost completely ionized, a plasma of electrons and photons, protons, dark matter and neutrinos, to being largely neutral hydrogen and neutral helium. And the CMB emission encodes information about that primordial plasma, plus perturbations, which we believe were inherited from the epoch of inflation. It gives us, again, tells us a bunch of things, but among other things, it gives us by far our most accurate measurement of the dark matter density, and is probably our best single piece of evidence that dark matter or a component like dark matter exists in the universe. This is a very old plot from Wynne, whose website. This little movie is just going to show what the CMB power spectrum would look like as you change the amount of dark matter in the universe. You see the variations in these different peak sizes give you a sensitive probe of how much purely gravitationally interacting matter there is versus matter that also experiences radiation pressure. You can match up this curve to what we actually observe. We have now measured thousands of modes in the CMB with good accuracy, and that gets you an answer that that gives you this percent level measurement for the amount of dark matter in the universe, which is where our statement comes from, that it's about 5/6 of all the matter. Okay, so that's the baseline thing that the CMB taught us about dark matter. What more have we learned, and can we learn? So the CMB can set a stringent, so CMB can do a lot of things. This is a limited survey. The CMB sets a stringent limit on the effective number of relativistic degrees of freedom around recombination. In the standard model, we expect this to be just a hair over 3. This N effective is measured with Planck to be 2.99 plus or minus 0.17. You can bring in information from other CMB telescopes. My understanding is at the moment they all look pretty consistent with the standard model and with this error bar that is around the scale of 0.2. That's a pretty powerful constraint. It tells us that during this epoch, most of the universe's energy density, even most of the universe's energy density and most of the universe's energy density and radiation was contained in stuff that we already know about. These constraints can be generalized to talk not just about new fully relativistic degrees of freedom, but light but massive relics. And my colleague Cora Dworkin and her group are the world experts on that direction. The CMB sets stringent constraints on how matter-like does the dark matter look. Is its equation of state really redshifting, really behaving the way that you would expect from pressureless matter? This is a paper from a few years ago that put together CMB data and large-scale structure data to just ask, if you allowed the amount of dark matter in the universe to vary over time, how tightly can you constrain that? This region, so this A here is 1 over redshift. This region around here corresponds to around the region where the CMB was emitted. Everything looks pretty consistent with lambda CDM, and this region between matter radiation equality and the CMB redshift is the time when that is most tightly constrained. Related to that, you can test the possibility. You might ask, well, okay, the dark matter was 80% of the matter in the universe at the CMB epoch, but is it still? What if some of the dark matter has decayed since that epoch? even, I'll talk later about what happens if that dark matter was decaying into visible things, but even if it decays fully invisibly, just from the gravitational effects that this would have from the distribution of dark matter, constraints from the CMB and large-scale structure, which are dominated by the CMB, can say you can't have had more than a few % of the dark matter in the universe at the CMB epoch decay by the present day. The lifetime has to be 2 orders of magnitude longer than the age of the universe. So the CMB tells us both that the dark matter is there, that it's 80% of the matter, and that it's pretty matter-like as best as we can measure it. And its abundance has not changed very much since that time. A thing that has less to do, maybe less to do with dark matter, but is of course an important probe of the CMB for new physics, is that the CMB sets stringent limits on inflation. This is not my specialty area, and there are people in the room who it is their specialty area, but I will just give you the broad summary. The CMB already sets stringent limits on the scalar amplitude and spectral tilt of the primordial power spectrum of density perturbations. This is a paper from a couple of years ago showing the forecast of where we currently are with this light blue region is like current bounds on, in this case, the axis is the tilt of the primordial perturbations, which gives you insight into inflation models, and the tensor to scalar ratio, which can be measured or constrained at the moment by looking for B-mode polarization in the CMB. And then these various dots and lines correspond to the space populated, and this blue band here correspond to the space populated by different inflationary models. These inner colored regions show how much better you would expect to do with future CMB experiments. So of course, some years ago, there was a lot of excitement about the possibility that maybe we had seen primordial gravitational waves or tensor fluctuations, which would be a very clean probe of inflation via B-mode polarization in the CMB. The BICEP results turned out to go away, turned out to be dust contamination. These measurements are difficult, but this is still a major target for upcoming instruments, and I will talk a bit more about where we're going next with CMB observations. There, you can have non-trivial interaction dynamics during inflation that would give rise to deviations from the Gaussian random field. Again, we haven't seen non-Gaussianity in the CMB. That and large-scale structure provide stringent constraints on this. But so this is another possible, fairly general probe of things that could be different from the simpler single-field models of inflation. And if there are new particles, my colleague Shobhit Kumar, who was here earlier and who has now headed out, has done a lot of really interesting work on cosmological collider probes of new particles and new energy scales during inflation, which can also imprint themselves on the perturbations that we measure in the CMB and in large-scale structure. If we go back to dark matter, one very generic thing that could happen in the physics of dark matter, even if it does behave exactly like matter, is that there might be new scales in the dark matter distribution imprinted by dark matter physics. And now this relates to what Mark's talk was about earlier, which unfortunately I missed, so I'm just going off the abstract, that one of the common modifications to the microphysics of dark matter is that it would change how dark matter is distributed in the universe on small scales. Now, the CMB is not the best measurement we have for small scales. This upper plot is showing a set of constraints on a particular class of dark matter scenarios that would have that property, where the dark matter is just extremely light and has a macroscopic wavelength. So this is mass scales 10 to the minus 18 eV down to 10 to the minus 33 EV. At the constraints that are most powerful at like the upper end of this mass range, so where we would usually say, there's a fuzzy dark matter bound that no more than that 100% of the dark matter in the universe cannot be lighter than 10 to the minus 18 EV. These are not coming from the CMB. These are coming from astrophysics. These are coming from black hole superradiance in this purple band. These are coming from stellar clusters like Eridani 2. These are coming from observations of small galaxies and small halos. Looking on small scales is unsurprisingly powerful for looking at changes to the dark matter distribution on small scales. But if you consider the possibility that maybe some subfraction of the dark matter is in this form, then on small scales where everything is pretty nonlinear, it's hard to tell if only a small subfraction of the dark matter is doing something strange. But on large scales, where we have the CMB and where we have large-scale structure data, we can actually make very precise measurements and constrain small subfractions of the dark matter doing something unexpected at the level of 10 to the minus 2, because the CMB gives percent level measurements. So this like light blue region over here in this plot, where some small fraction of the dark matter has an extremely light mass, the strongest constraints are actually coming from the CMB. And in general, if you have something that modifies the properties of dark matter on large scales, the combination of CMB and large scale structure is likely to be where you do best. Another example of dark matter physics that can have that effect is scattering between the baryons and the dark matter. Again, the question here is, well, if we have scattering between baryons and dark matter, it will affect things at a range of scales. This is from a plot from last year. These different colored lines are showing the effect of turning on scattering between baryons and dark matter. So this is non-gravitational scattering now, some kind of new interaction. This with different velocity dependencies. So the idea is that the cross-section here scales as v to the n, where n goes from -4 to 4 across this plot. -4 is the scaling for Rutherford scattering. You can get a range of these scalings in simple particle physics models. And you see that these different scenarios lead to, this plot is showing the suppression in the power spectrum of dark matter as a function of scale. High end of this plot is small scales, low end of this plot is large scales. The CMB basically has sensitivity to stuff on this side of this dashed line. Large scale structure gets you a bit further. Observations of the smallest dark matter halos get you further out to this side. And again, what you see is, for a lot of these models, there's a big effect at really small scales, but there is a small but still measurable effect at large scales, and the CMB is really precise. And in particular, for scenarios like this Rutherford scattering, like scenario where the signal is very enhanced at low velocities, then the CMB can be very powerful. Okay, so these are all things that these are all kinds of physics that affect the anisotropies of the CMB, primarily through affecting the behavior of the fluctuations. Our key tool for modeling these, if you want to test, okay, I've got a cool model, how does it show up in these signals? The CMB is on large scales where things are pretty linear, and usually cosmological perturbation theory works very well. And so the good news, if you want to do this, is that there's been a lot of work already to both write public codes that implement cosmological perturbation theory for the CMB and to add new physics modules into those codes. So there are long-standing public Boltzmann codes called CAM and CLASS that solve for the global ionization and thermal history and forecast observables for the cosmic microwave background anisotropies and for large-scale structure. These have been optimized to be pretty fast. They can be coupled to Markov chain Monte Carlo codes for scans over parameters, and there's a pretty large literature on how to implement various forms of new physics into these codes. I didn't put it on the slide, but our colleague Siddharth Mishra Sharma at BU had a blog post recently about using agentic AI to both build on these codes and to try to add extra stuff into these codes. So that maybe that will make this even easier in the future. But there has already been a lot of work done on this front, and if you have an idea for new physics you should test, and this is probably the first place you should start is, all right, what is already publicly available for me out there? There's also been a lot of work in recent years going beyond sort of linear cosmological perturbation theory to go to higher order and into the mildly nonlinear regime, which is particularly important for large-scale structure, using effective field theory methods. There are a bunch of public codes associated with this. My colleague Misha Ivanov over at MIT is a real expert on this, so these tools can also be very helpful. Okay, so this is a nice pipeline for so most of what I've told you about here as it pertains to dark matter, the signature is this new physics modifies how dark matter is distributed in space or in time. So it like changes the distribution of dark matter on the sky, or it changes how dark matter evolves through cosmic history. The CMB is a good probe of that. But it's also potentially a good probe of other things. So as well as these changes to how the dark matter is distributed, another kind of physics that you might expect is maybe the dark matter, well, we mentioned in the case of scattering, maybe the dark matter has non-gravitational interactions with the standard model. Maybe there are non-gravitational channels for transfer of energy and momentum between the sectors. In that case, the CMB can also be quite sensitive to the downstream effects of those energy transfers. And now we are getting into stuff that I personally have spent a lot of time thinking about. Now, as we've said, if you want to modify the dark matter distribution and have an observable effect on the CMB, you generally need a non-negligible fraction of the dark matter to participate at some point in cosmic history. The CMB is very accurate, it's great, but the accuracy is like percent level. So if 1% of your dark matter has a very long wavelength or is scattering intensely or is doing something exciting, the CMB can potentially give you a handle on that. If 10 to the minus 10 of the dark matter is doing something weird, then you're not going to learn about it from looking at the dark matter distribution in the CMB, generally. However, if 10 to the minus 10 of your dark matter is doing something that produces standard model particles, we are a lot better at detecting standard model particles than we are at finding dark matter, and that can potentially have significant effects on the CMB. So I want to talk about some things in that category. So I will say that for the dark matter standard model elastic scattering example, in that case, you both have changes to the dark matter distribution, and you have things that like change the photon backgrounds, changes to the gas temperature in gas clouds. Those constraints are often actually comparable to the effective changes to the dark matter distribution as measured by galaxy clustering. There's not a large hierarchy in that case. But this is not the case for all signals from dark matter interactions, and in particular, if I can get access not just to the kinetic energy of the dark matter, but all the energy stored in the mass of the dark matter, there's a lot of energy there. If there's a process that liberates that, you need only a small amount of dark matter to undergo that process for it to have big effects. So let's just do the back of the envelope calculation of what I have there. So the total energy stored in dark matter, or it could be multiple dark matter species, so in some non-relativistic dark sector, is about 5 GeV per hydrogen atom. That's what we mean when the CMB tells us that 5/6 of the matter in the universe is in dark matter. So suppose we can liberate that mass energy. How much can we do with 5 GeV per hydrogen atom? Well, the amount of energy that you need to ionize a hydrogen atom is 13.6 eV, okay? So that's like 10 eV. So if I have 2 times 10 to the minus 9 of this 5 GeV per hydrogen atom budget, that's enough power to ionize all the hydrogen in the universe. If all the hydrogen in the universe had gotten ionized after the CMB was released, we would definitely have noticed. The observations of the CMB are actually powerful enough that you can tell if a few hydrogen atoms in 10,000 were ionized at the time shortly after the CMB was released. So that is suggestive that this probe will be able to study, taking a fraction of this dark matter energy, putting it into ionizing particles at a level around 10 to the minus 11 or 10 to the minus 12, which turns out to be the right answer. If you wanted to heat up the gas, suppose I wanted to heat up all the gas in the universe by 10,000 Kelvin. It takes about 1 electron volt of energy to heat a 1 GeV hydrogen atom by 10,000 Kelvin. That's 2 times 10 to the minus 10 of this energy budget. For much of the universe's history, we might not have noticed if the temperature went up to 10,000 Kelvin, but this is about where the constraints are from the Lyman alpha forest, for example. If we wanted to perturb the CMB itself, so we have a limit from Kobe-Faris, which I'm going to say a lot more about in a few slides, that the CMB blackbody spectrum is a beautiful blackbody to a precision of about 10 to the minus 5. If we wanted to ask, okay, how much of this power do you need to perturb the CMB? In the present day, so matter radiation equality was at about redshift 3000. In the present day, the ratio is a few thousand between matter and radiation. So if I want to perturb the CMB at the level of 10 to the minus 5, that means I need about 10 to the minus 8 of the density in matter to perturb the peak. You may notice that this number is kind of large compared to these two numbers. This is why often for these energy transfers, at the moment, the anisotropies are a stronger probe than looking at the blackbody spectrum, but that could change in the future. Okay, now the idea of using these kinds of observables to probe mechanisms that let you take energy stored in the dark matter mass and turn it into visible particles, such as through dark matter decay or annihilation. This is not new. This goes back, the earliest paper I'm aware of was in 1998. And it's also very similar to indirect detection. For indirect detection, similarly, if you convert energy stored in the dark matter mass into visible particles and then you go look for the visible particles in the sky, that's the entire indirect detection program. And again, you don't need very much of the dark matter to annihilate for that to be a signal. So this is very complementary to searches that look at the changes to the dark matter distribution. In cases like this, where you're seeing a visible signal, probably there is basically no impact on the dark matter distribution from the viable parameter space. But you have to have some mechanism that lets you get the energy out of the dark matter and turn it into standard model particles. If that mechanism isn't there, then you can fall back on the dark matter distribution probes. Okay. And the difference in the elastic scattering case, it's much more comparable between the gravitational probes and looking at the standard model side of things, because we only have access to the kinetic energy, not the mass energy. The dark matter is pretty non-relativistic today. It's got a lot less kinetic energy than mass energy. Okay, so we can ask, all right, so if you've got any kind of dark matter scenario, like these fun extra dark dimension scenarios where dark matter is decaying or annihilating or black holes are evaporating or otherwise converting their energy into visible particles, you may expect some fairly substantial effects on the history of the universe, and we can ask what the CMB tells us about that. Okay? So if you want to do this calculation at better than the back of the envelope level that we did, you actually have to do a calculation for if I throw an energetic standard model particle into the universe, what happens to it at early times. Fortunately, I and other people have, again, written public codes to do this for you. You don't have to recalculate it yourself unless you're doing something particularly exciting. So the generic behavior is that if I throw a high energy particle into the early universe, which is dense, which is hot, it will generally interact with the background and have a cascade of interactions that produces a bunch of secondary particles. Those secondary particles can produce extra ionization. If they're above the ionization threshold, they can heat the gas. They can distort the blackbody spectrum of the CMB. This is all modeled like the one that my group wrote and that thus is my favorite is this dark history public code. And so this can give you modified thermal and ionization histories, and the more recent version of the code also computes distortions to the blackbody spectrum. Dark history is really meant to look for relatively high energy stuff, so stuff that's injected above the ionization threshold. If you're only injecting particles around the CMB energy, there are other codes that are available. You don't have to worry about a lot of these cooling processes. This paper by Acharya et al. Has a nice discussion of like soft photon heating and the absorption of very low energy photons, which can also have big effects. Okay, so suppose I have taken one of these codes and I have run it, and it has told me how the ionization history will be modified or how the temperature history will be modified as I throw in as I add these extra particles. And I will say also that these codes are pretty versatile. If you know what your model is injecting, like what are the particles, what is their spectrum, and when did you inject them, that's all you need to know. They have built it, like dark history has built-in functions to do dark matter annihilation or decay to any standard model particles. But if you want to say, I have a weird spectrum that doesn't correspond to any two-body standard model final state, that's fine. You just need to tell it the spectrum. If your spectrum is changing with respect to redshift, that's fine. You just need to tell it how your spectrum changes with respect to redshift. If you have a redshift dependence that is not the normal dependence from dark matter decay or annihilation, again, that's fine. Like, it will mean that you don't get to use the built-in functions, that you need to like add your own little function that tells you when did you inject the particles with what spectrum and what particles. But do that and it will do the whole calculation for you. Okay, so for CMB anisotropy, as far as we can tell, the best probe by far is if you're producing ionizing radiation, ionization is likely what you're going to be most sensitive to. So as we said, the CMB anisotropies have been beautifully measured by a range of experiments, and after the CMB is emitted, we expect that the universe is pretty close to neutral, like has very few ionized particles, down to around redshift 30. The ionization level should be as low as a few times 10 to the minus 4. So the cartoon picture here is we've got the CMB. These CMB photons are just flying happily, free streaming through the universe of neutral hydrogen and helium, coming to our detectors at the Planck telescope. If we have extra electrons around, then they get in the way. They will scatter those photons. They will modify the pattern of anisotropies in this period between when the CMB is emitted and when the universe starts to reionize at later times. So you can take your modified ionization history from dark history or similar and run it through this class or CAM, one of those similar codes, and ask how would this change the CMB. And right, so this is just an example of what one of those inputs from dark history looks like. It's provided with a bunch of example notebooks. When you run dark history, one of the outputs that you will get is something like, here is the modified ionization history. This is an example for annihilating dark matter. This dashed line is the baseline. These solid lines are showing what happens as you turn on energy injection. The yellow line is the full calculation. The blue line is an approximate version. You see and that approximation is going to come up on the next slide. This approximation is basically, do you take into account that there were earlier energy injections in the universe, or can you assume that the problem is basically linear and your particle cascade doesn't depend on anything that happened earlier? For ionization, you see that is actually a really good approximation, and that is helpful for doing these calculations fast. So you run dark history, you'll get outputs like this. This is your ionization history. This is your temperature history. For a non-CMB, the CMB is not very sensitive to the gas temperature, but if you want, the spectral distortion of the CMB is potentially sensitive to the gas temperature. The anisotropies are not. But, so given this temperature history, you can potentially plug this into constraints on the temperature from the Lyman alpha forest or perhaps in future cosmic 21 centimeter. So you can then, this has a weird animation. Sorry, that was supposed to be just up here. So, all right, so if I say, okay, so I can take this dark history ionization, I can run it into class, that will tell me how I change the CMB. you can certainly do that. You can do this for any model. This is reasonably straightforward. But if you want to run this through a Markov chain Monte Carlo and ask about the degeneracies with the cosmological parameters, well, so there are two ways to do this. One is to do a Fisher analysis, like just look at how these energy injections perturb the CMB, figure out what the derivatives are, do a Fisher forecast. There's information on how to do that in the literature. But if you want to run a Markov chain Monte Carlo, you have a problem, which is that class is fast, but dark history is very slow. Fortunately, because of that approximation that I just mentioned to you, that the particle cascade doesn't really depend on what has happened previously, you can take an approximate approach where you model the problem as linear and say, okay, if I have an energy injection at this time, an energy injection at this later time, where I have the sum of two energy injections will have basically the same effect as working out the effects of those energy injections separately and adding them up. And so this approach is implemented in the exoclass module of class. I mentioned earlier, class has a bunch of modules to do modified physics. So you can use this to implement basically an approximate version of dark history. And the way that this works is you can use dark history and these results have all been run and tabulated for energy injections between about the keV scale and the 10 TeV scale. If you want to go outside that, you would have to run the code yourself to expand these tables. You can compute how a single particle injected at a given redshift subsequently deposits its power into heating, ionization, and low energy photons. And then to the degree that the problem is linear, you can basically just take linear combinations of that to figure out what the net effect will be for your arbitrary spectrum of particles injected with a given redshift dependence. So, and fortunately, taking linear combinations is super fast. So having pre-computed this table, and I've done that, it's in the literature, but you could also do it yourself, starting from dark history or a similar code, then in any given run, you will just say, okay, I'm going to take a linear combination of these energy effects, feed those extra source terms into the evolution equations in class and CAM. That will get you your modified ionization history and is very quick. So then with that, you can use class or CAM and its connection to Monte Carlo codes like MontePython or CosmoMC to figure out how these energy injections actually appear relative to the likelihood of Planck of a similar experiment. And so people have used that to set nice constraints. These are mostly older results, but people have used that to set nice constraints on the annihilation of particle dark matter, also particle dark matter decay. This is a plot showing the limit on the cross-section for annihilation as a function of the dark matter mass. And while this plot cuts off at like 5 GeV, actually these constraints go down to the keV scale and really to the sub-keV scale. They go almost unchanged down to the ionization threshold. As I said, the existing tools work pretty well for 100 TeV to 10 TeV particle injections with an arbitrary redshift and energy dependence. So if you have a neat dark dimension model where the dark matter mass scale is changing over time and its decay lifetime is changing over time, you can adapt these tools to do that. This is from a plot showing an example of cases where you make some axion-like particles just irreducibly due to freeze-in processes, and then subsequently they decay. And this band here is showing the CMB constraint that you get in that parameter space. You might ask what happens below 100 EV, or above 10 TeV. So below 100 EV, we have all the tools to do in dark history, just the results haven't been publicly tabulated to the same degree. The latest version of dark history is capable of properly handling injections below the ionization threshold. There is still a signal below the ionization threshold, but its properties are pretty different to what happens above the ionization threshold. It basically comes from ionization of already excited hydrogen atoms or excitation of hydrogen atoms that can then more easily get ionized right around the epoch of recombination. So it's much more peaked around the time of the CMB release than other signals. We studied this with a student in a paper a couple of years ago. Okay. So these are nice limits. These work very broadly to constrain a range of dark matter models because this is essentially just a calorimetric bound. Mostly you're just measuring how much power did we dump into ionization. Okay, so you might ask, okay, where are we going next with this? So we have a new big CMB experiment. The Simons Observatory has begun its science observations. It started running in 2025. It is meant to run through to take data through 2034. This is a recent paper that has a discussion of science targets and what they'll be able to do once they upgrade their largest telescopes, which is planned for the next few years. And this is just taken from this paper, a table of some of the science goals for the Simons Observatory. So these are current limits on the slope of primordial perturbations, like we talked about earlier. This is that FNL local. This is a measure of non-Gaussianity. This is the number of effective relativistic degrees of freedom, the CMB epoch. These are proposed limits on neutrino mass. And this is the Simons Observatory forecast for what they're going to be able to do. And in particular, I'm pretty excited about this low N effective number because, again, this will give us a precision measurement of are there any light relics lingering around from the early universe, even at a temperature below the standard model temperature. That's it. It will do better in some constraints than others. This is a paper from last year, which I am not on, but it was coincidentally written by an undergrad, led by an undergrad advisee of mine, Charlotte Myers. She is great. So this pink line is showing where these, so this is an example for dark matter annihilation to muons. This current line is where the current limits are. And this green line is showing what you would get with a hypothetical CMB-S4 experiment. Unfortunately, as we heard, CMB-S4 has been cancelled, but the Simons Observatory will get a good part of the way there. And this black line is showing sort of your ultimate cosmic variance limited experiment. And you see these lines are not actually that far apart from each other. Like maybe with a lot of work, you can eke out another sort of factor of 2 to 3 in sensitivity here. The reason for that is that a lot of the changes based on changing the ionization history happen at pretty large scales, so pretty small values of L. And those pretty small values of L, Planck has already measured really well. Our limiting factor there is what we call cosmic variance, which is just the statement that any universe is going to be a random realization of the initial conditions and the cosmological parameters, and we only have one universe to look at. So, you know, we can't like average over a large volume of universe to get down to the fundamental underlying parameters. It's just, you know, okay, we only have one realization to look at. So that we are going to kind of hit a limit on these dark matter annihilation constraints from the CMB. We are already pretty close to as well as we are ever going to be able to do. That said, especially for things where you can get information from smaller scale modes, the CMB will do better in the future, and large scale structure also gives us the possibility of being able to measure a lot more modes and at smaller scales, and that's also an area where there's a lot of very interesting data coming in. Okay, so in my remaining time, I want to talk not about CMB anisotropies, which has been the workhorse of cosmology for the last 30 years, but about a set of observations which we have largely ignored for the last 30 years, which are modifications to the blackbody spectrum of the CMB. But I guess because this is a bit of a change of topic, I guess I do want to pause now and see if anybody has any burning questions. Okay. And is this okay? And I hope that means that either people are following along and it's interesting, or that it's boring and you're just like move along, Tracy, as opposed to people being very confused. Yeah, I do want you to let me know if there's anything that you're confused about. Okay, so then let's talk about CMB spectral distortions. So this is a paper from 1996, which is now 30 years ago. This is a measurement of the intensity of the cosmic microwave background as a function of its frequency. And these error bars are 400 sigma error bars. Now, when I do data analysis in gamma rays, I would be overjoyed if my 1 sigma error bars looked like this, right? So, I mean, this is really an amazingly precise measurement. I was trying to find confirmation of this on the internet last night, but the internet claims that this is still the most perfect blackbody that we have ever measured 30 years ago. So we found then that the fractional deviation from a perfect blackbody at a temperature of about 2.725 Kelvin is less than 10 to the -5. And there have actually been some nice papers in recent years going back and redoing that data analysis a bit more carefully, which have managed to get us sort of a factor of 2 level improvement on those constraints. So that's very cool. Now, but you might say, okay, but like, should it be a perfect blackbody? I mean, if there was a lot of stuff going on in the early universe, is there nothing that could have distorted the spectrum? And the answer is no, actually, we don't expect it to be a perfect blackbody. We do expect there to be deviations to this. There are standard model deviations expected at the level of 2 × 10⁻⁶. So we already got pretty close to that point in the 1990s. And if you have mechanisms like what I just talked about, like dark matter decay, dark matter annihilation, anything that is moving energy around between the standard model and dark sectors, we would definitely also expect that to leave distortions in the spectrum. More broadly, these spectral distortions can be a sensitive probe of many kinds of novel physics, from primordial magnetic fields and gravitational waves, primordial black holes, topological defects, couplings between axions and photons, whether or not the axion is the dark matter. If there's a big enhancement to the small-scale power spectrum, that can give rise to distortions. If there's dark matter annihilation or decay or conversion, that can give rise to distortions. There's a white paper from 2019 that is a pretty good reference for these things, although there's also been work on them. There's also, of course, the field has advanced in the last 7 years. Okay. But as I mentioned, this is actually the latest data that we have on the CMB blackbody. When we have done all these beautiful subsequent measurements of the CMB anisotropies, these are all differential measurements. They're measuring what is the difference between the temperature on the sky here and here. They do not actually give us insight into what the monopole is. Okay. So you might ask the question, all right, so we should look for distortions. What kinds of distortions should we be looking for? So this is going to be like the general sort of spectral distortions 101 slide. Okay, so what kind of distortion you get depends on the redshift at which you perturb the CMB, because at high redshifts, the photons in the CMB are very efficiently and continuously scattering off each other and scattering off the gas. So even if you perturb them, that perturbation can get washed out pretty fast. In particular, at redshifts above about 2 × 10⁶, so temperatures much above the keV scale, there are efficient photon number changing processes. So, like photon comes in, scatters off an electron, 2 photons come out. Photon number is not conserved in these. In general, if you inject energy at these very high redshifts, what happens is any change to the spectrum rapidly thermalizes. You get driven to a thermal blackbody distribution with 0 chemical potential, and you don't expect to see any distortion. I mean, you will see a overall shift to the temperature of the universe, but it would be really hard to tell if just the universe is a little hotter than it would have been in the counterfactual case where this distortion didn't happen. The temperature is what it is. Now, below redshifts 2 × 10⁶, however, those number changing processes are not efficient. But the photons are still scattering a lot. They're still rapidly bouncing off the electrons. So in this period, Compton scattering is fast, so the spectrum is driven towards an equilibrium distribution, blackbody distribution, but it can have a non-zero chemical potential because it's the photon number changing processes that would drive the chemical potential to 0, and those aren't efficient anymore. So in this case, there's a sort of very generic attractor solution, which is shown by the blue dashed line here. So these are asking about differences to the This is the change to the underlying CMB spectrum. This is actually expressed as a Green's function. This is the change to the underlying CMB spectrum, so it can go negative. So this blue dashed line is the characteristic shape of a chemical potential, which we call a mu-type distortion. And this is kind of the generic indication of something messed up the CMB and perturbed it away from a perfect thermal blackbody in this epoch between redshift 50,000 and redshift 2 million. Now, on the other end of the scale, once you get below about redshift 10 to the 4, then photons around the CMB peak just do not equilibrate very quickly. At these lower redshifts, however you distort the CMB, it mostly just sticks around. It redshifts with the rest of the CMB, but you can measure that distortion at late times and actually learn quite a bit about what the initial distortion was. So you will sometimes see statements in the literature that at redshifts less than 10 to the 4, the distortion should be purely a Compton Y distortion. But that is based on the assumption that the initial distortion was a Compton Y distortion. I think the true statement is whatever the distortion is, it's more or less what you initially injected, redshifted to the present day. So the Compton Y distortion is what you would get if your mechanism is I heated up the gas, so it was at a different temperature than the CMB. And then the CMB scattered on the gas but didn't have time to fully thermalize. That gives rise to a Y distortion. That's the black line in this plot. You see it has a meaningfully different shape to the mu distortion. But in principle, you can have other kinds of initial distortions. In particular, if you have something like the secondary particle cascade I was telling you about, where I injected like 5 GeV B quarks into the universe at early times, when they produce secondary photons as they cascade, those secondary photons can give you a high energy tail on the CMB, which doesn't look like a Y distortion. Now, you'll note there is a gap between these two redshift ranges that I just stated. In this sort of intermediate range between redshifts, between about 10 to the 4 and 10 to the 5, you get something in between these. So partial thermalization can occur. You don't completely retain the initial distortion. It gets sort of shifted towards a mu distortion, but it doesn't get all the way there. So these other lines here are basically showing the like interpolation between a mu distortion and a Y distortion. So when people quote constraints on spectral distortion from COB-FIRES, usually they test these mu-type distortion and Y-type distortions, and sometimes they test the intermediate distortions. But that's how the limits are typically quoted. But again, in principle, the distortion can be quite a lot broader than that if you inject if the injection happens at late times. Okay, so a couple of years ago, my colleagues and I upgraded. Yeah,
so
please.
All these processes we were talking about, they happen with standard physics?
Good.
So then you give some background.
Yes, that's right. So there are standard model sources of both mu distortion and Y distortion. And I'll say a little bit more about what those are at different scales. But yeah, in principle, there are standard model sources of both of these. So yes, so in particular, I am interested in things that don't look like a mu distortion or a Y distortion and may have no standard model background, because then you can hope to use spectral information to tease this out from the expected standard model signals. Although, like, there's an expected size of the standard model signals, and in particular for mu distortion, that expected size is quite small. So like, if we saw a mu distortion that was 100 times larger than the standard model prediction, that would signal non-standard model physics, even though you can get a mu distortion in the standard model. Okay, so a few years ago, my colleagues and I upgraded our dark history code to allow computation of the full spectral distortion from arbitrary injections of particles. I've said high energy ionizing particles, but I mean, it works for more or less anything above the CMB peak. It doesn't include some processes that are needful when you inject photons below the CMB peak. So it tracks all the secondary particles produced by the cascade as particles lose energy. It also focuses on the epoch after recombination. There's previous work in the literature on pre-recombination signals. So these are a couple of plots from those papers. This upper panel is showing one example of a kind of distortion you get from this cascade in the black line. So the purple and yellow and pink lines here are different sources of standard model distortions at the expected level. And the black line is what you would have gotten from one example decaying dark matter model. So, and the point here is basically just the shape is different, the peak is lower, but there are areas where this distortion could potentially stand up pretty strongly from the standard model backgrounds. This lower panel is then just showing what happens. I mean, it's dark history, so you can run over all kinds of injections. This is showing for dark matter decaying to electrons and positrons, so that's just one example channel. As you vary the mass of the dark matter particles, so the energy of the initial injection, and force it to be sort of around the limit that you currently have from the CMB anisotropies, what kind of each of these lines corresponds to a distortion that you would get for a different dark matter mass. And again, you see there's often this kind of high frequency shoulder that looks pretty different from what you would expect from the other kinds of distortions. And there's different spectral shape, and there's also variation between like different dark matter models. So in the dream case where we actually could detect this, it wouldn't. So the CMB anisotropy measurements I told you about before, they're super general because they're really just colorimetric. They're basically just asking how much power did I put into ionization during the cosmic dark ages. So they're great for constraints. But if we saw a signal there, we've demonstrated quantitatively that essentially like all annihilating dark matter models look the same in the CMB up to rescaling on the total amount of power going into ionization. They all look identical. So it's amazing for general constraints, but if you actually saw a signal, you would get one piece of information. This, I mean, it's going to be harder to see. The calibration of these scales is below the 10 to the minus 5 level from COB-FIRES, so we didn't actually get a new constraint from doing this analysis. But if you could see them, there's potentially a lot of information in this spectrum. Okay, so I have some work in progress that I just want to mention to you because, as previously, if we wanted to actually run a likelihood analysis with these and do forecasting, you would run into the issue that dark history is very slow, which I mentioned earlier. But I told you earlier that the solution to that in the context of changes to the ionization and temperature history is this module called exoclass that basically makes a linear approximation. So we are working on building an extension to the, so the class code also has stuff in it to study the pre-recombination spectral distortions that are a combination of mu and y distortions. So we have work in progress to build an extension. So first, like an interface that just class talks to dark history to model spectral distortions across the full redshift range. And so we've been calling that the slow interface, very creative, but to also build a fast interface that uses a similar linear approximation that exoclass uses, but now for spectral distortions. So you can pre-compute the distortions from a basis of energy injections, take linear combinations, and that will let us scan over the whole space pretty rapidly. Now, of course, I told you it works for ionization history because the back reaction effects are small for ionization. Like that, this linear approximation is a good approximation. So one thing to make this fast thing work would be, is it actually small in this case? And if it, is the problem actually linear? And if it wasn't, we would have to do something more creative, like maybe using some kind of emulator to try to mock up our slow but accurate dark history code. It turns out that in this case, if you break the distortion into a Y distortion part, because as we talked about before, there is some change to the gas temperature, so there is going to be just some automatic Y distortion coming from that heating of the gas. But if you break the distortion into a Y distortion part and a residual non-Y distortion part, then it turns out from testing this explicitly, for scenarios that are not already ruled out, the residual part is really linear with respect to the energy injection. So we can just take linear combinations, and that's fine. These plots are just showing some examples of that. I will say these plots have a bug at the low frequency end, which we are in the process of rerunning everything to fix at the moment. So take the big preliminary notice here seriously, but this high frequency tail should be correct. So these different lines correspond to basically what you would get by considering a decaying dark matter model, multiplying or dividing the lifetime by a factor of 100, and then rescaling the final result by that same factor of 100. So if the lines overlap, it means that things are linear. And you can see that in this tail, the lines generally overlap really well. The forthcoming experiments are trying to measure the spectral distortion around this range, so there are differences out at extremely high frequencies, but that's probably not somewhere we can measure. That's for a decay example, and that's for an annihilation example. Now, the Y distortion piece is not necessarily linear with respect to energy injection, but it also has a giant standard model background. So our current plan is basically just to marginalize over that Y distortion piece and not worry too much if we get its normalization a bit off. Okay, so class already has tools in it to do sensitivity forecasts for upcoming experiments. So we want to, get this pipeline running, do some sensitivity forecasts for simple cases, and then do a public release so anybody can figure out the spectral distortion from their favorite energy injection model. Okay, so then, all right, so in my remaining 5 to 10 minutes, I just want to say a little bit about, yeah?
So you said the standard model background for Y distortion, big-ish?
Yeah.
So what kind of level of?
Yeah, this is a good question. This is exactly what I'm about to talk about. Thanks. All right. So I want to talk a bit about the prospects for detection with where things are going experimentally, since as I told you, we haven't measured this experimentally for 30 years, and what the backgrounds are. So the guaranteed standard model spectral distortions, reionization is expected to generate a Y distortion at the level of 2 × 10⁻⁶ in these units. And again, the Kobe-Firass limit is a little below 10⁻⁵. So we're actually only a factor of a few away from hopefully being able to see the distortions in this. This is, right, so on this plot, this black line is the expected Y distortion from reionization. So this is a plot from Kluber in 2016 about expected standard model sources of spectral distortion, and this is the big one, this is the Y distortion. Now, the expected mu distortion is much smaller. As I understand it, the leading expected contribution to the mu distortion is that the small-scale tail of the CMB anisotropies, okay, now this is going to be a bit technical, non-experts do not have to worry about this. But if you think about the tail of the CMB, at large scales, the CMB anisotropies get damped out through a process called self-damping. The energy, the power that was in those perturbations has to go somewhere. Where it goes into is spectral distortions. That spectral distortion does not actually have exactly a mu shape or a Y shape. It's generated around the time of recombination, so it's pretty late, and in principle, it could be different. But you can show that to a pretty pretty good approximation. You can decompose it into a part that looks like mu and a part that looks like y, which are of the same order. So the part that, and that order is around 2 × 10⁻⁸. So the part that looks like y is completely swamped by this reionization contribution. But the part that looks like mu, this is our understanding of sort of the guaranteed standard model distortion. If you do not see, if you get down to the sensitivity and you do not see that mu distortion, it means that something is different than we expect from lambda CDM in the in the small scale high K tail of the CMB. So that would also be pretty interesting. So most of the experiments that have been proposed are sort of aiming to target either this or this for their science case. Obviously, this is easy. This is easier. This is harder. Okay, so I want to just talk a little bit about the various experiments. So there are some ground-based experiments that may, so after, yeah?
The mu, it's an energy scale, right? So this is electron volts or?
So, sorry, are you, this number? So like this is, you can think about this as like, you can think about this roughly as how much energy is there in the distortion relative to the entire CMB. So so in this, this is like a ratio. Yeah. So I mean, you could, that's right. I mean, you could translate it into the chemical potential, but yeah, but people typically frame it in this way, which is dimensionless number. Okay, so in terms of upcoming experiments, so again, we haven't done this for 30 years, but there has actually been a lot of activity, particularly in Europe, over the last few years to try to get a measurement of spectral distortions. So the Tenerife microwave spectrometer, this is not really a CMB spectroscopy experiment. This is focusing on the radio background and on frequencies well below the CMB peak. But that's it. It's currently being installed. It's right around the corner. If there is something very exciting happening at frequencies well below the peak is about 200 gigahertz, then then this could potentially tell us about it. For those of you who know about the arcade excess, this is partly trying to test the arcade excess. The cosmic monopole observer is the first thing in here that I would say is really attempting to constrain spectral distortion around the CMB peak. They're planning to have 2 observing windows around 110 to 170 and 200 to 300 gigahertz, so above and below the peak, starting in 2030. And their target is they want to see that reionization signal, that y equals 2 × 10⁻⁶. Going further forward into the future, there's a proposed balloon experiment called BISO, and this would in principle be a pathfinder for a possible further future satellite version. I'm going to show you a plot at the end of this that shows the sensitivities of all these experiments, but this is just the outline of what they're doing. So this was confirmed a couple of years ago for 2 years of phase A funding by France. People have told me that it is confirmed to go ahead and build, but I have not actually been able to find official information on that on the internet. So, take with, possible question mark. So Cosmo just wants to try to see the Y distortion at all. BISO's main science target is aiming to detect that Y distortion from reionization at 5 sigma. It's going to be a really broadband experiment. It's aiming to cover frequencies from 90 to 2000 gigahertz with a fine 15 gigahertz resolution. So the goal, this would be a balloon experiment, and the goal is to have a technical flight in, I think, 2029 and aim for 2031 for the science flight. So these are things that could happen on the time scale of the next 5 years. Yeah.
So will they be sensitive to the reionization history or just some total number?
I mean, the Y distortion mostly just gives you a total number, I think. I mean, it would be a useful total number to have, but yeah, I don't think it tells you that because, I mean, so long as everything stays non-relativistic, then the Y distortion has pretty much a shape that's independent of how much energy you put in. So I think you do just get one integrated number. If you get to the point where you have relativistic corrections, then you could potentially measure that in the spectral shape, get some information from that. The relativistic corrections happen all the time when you're injecting 100 GeV dark matter particles, but they probably don't happen very much in the reionization context. It's a good question. So then beyond the balloons and the ground-based experiments, then you get into the more ambitious, okay, what if we could do a satellite experiment? So the satellite experiment that, as far as I know, is most on shell at the moment is this idea called fossil. So this is kind of similar technology to BSO, but you would put it on a satellite. Both are based on this earlier concept called PIXI that has been proposed to NASA several times, and NASA never really nibbled. But Europe appears to be at least somewhat interested in fossil. So this was proposed as part of a call from ESA. In October 25, it passed the first down select for the ESA planning process, which was the phase 0 selection. So in fall 2027, there's a phase A selection stage. If all goes well, the target launch date would be 2041. So this is definitely further out, but it's not infinitely further out. I still expect to be working in the field in 2041. There's also an alternate proposal called Spectre by a US team. This, as far as I know, is less on shell, but this would have better sensitivity. This is really trying to optimize different technologies for different frequency bands to get down as far as we could. And both fossil and this Spectre idea, the real aim would be to get to this mu distortion, would be to see this 2 × 10⁻⁸ mu distortion, or confirm it's not there, in which case that's really interesting. And if you can get down that 3 orders of magnitude, there's potentially a lot of other interesting stuff there in the meantime. So this is a plot from people in the fossil collaboration showing the expected sensitivity of these different experiments. So although I think they may be underestimating BSO a little bit at the high frequencies, this is the existing FIRES bound. They have BSO having this big drop here. I've seen other stuff from BSO that sort of includes this improved sensitivity more up into these higher frequency bands. This is the TMS one that I first met. So these little boxes are the ground-based telescopes that I mentioned. This solid blue line, this blue line here is the expected size of the Y distortion signal from reionization. So yeah, BSO and Cosmo are really aiming to get at that. If you could get down to so then the expected and the relativistic corrections to the Y distortion of these green lines here, so they're about another order of magnitude or 2 lower. And then down at the 10⁻⁸ level, this orange line is the mu distortion, and that's the target for fossil. Now, and just out of interest, if you take that set of decaying dark matter models that I talked about earlier that are currently at the limit from the CMB anisotropy bounds, and you ask what would those distortions look like relative to the sensitivity plot, then in my stupid physics by keynote plot, they look something like this. So I mean, already BSO and Cosmo might be able to say something about these kinds of distortions. If you get all the way down to fossil, there's a fairly broad space of models that could potentially be tested. Although, but by this, that's just based on naively comparing these sensitivities. To do this for real, we would need to do a proper foreground model and see, how degenerate these are with possible foregrounds. Okay, so that's the that's sort of the roadmap at a glance for going forward. The for what these various experiments would be trying to do over the next 15-ish years. This part of in Europe, many of these ideas were proposed, or similar things were proposed as part of this Voyage 2050 call that they did a few years ago. And one of the results of the Voyage 2050 call was that the ESA did put a big CMB spectroscopy experiment on its wish list for a small number of big projects on the 2050 timescale. So that's one of the things that has motivated all this activity in Europe. Okay. So I think that's. I think I'll stop there. I'll take a few questions. But yeah, I hope I've told you. The CMB's already told us quite a lot about dark matter. It can provide stringent tests of the large-scale structure of dark matter. It can tell us about new light relics, and it can tell us about energy transfer between the dark sector and the visible sector. I have done some advertising for our public code, which aim to model one class of such effects, injecting non-thermal standard model particles into the early universe. And I hope I've persuaded you that if you want to do these calculations, it's not that hard, and we are happy to give advice. Measurements of the anisotropies can already set stringent bounds on a pretty broad class of annihilating and decaying dark matter models. And in spectral distortions, we haven't measured it for a long time, but the good thing about not doing a measurement for 30 years is that when you come back to it, you can potentially improve things by 3 or 4 orders of magnitude due to improvements in technology. And there are prospects for a range of distinctive signals in those instruments. So I'll stop there. Thanks.